Yes, sir. Good morning, everyone. Welcome you all to the short-term course and faculty development program, AMCDDRP, conducted by the Department of Electrical Engineering, National Institute of Technology, Rourkela. The speaker of the present session is Dr. Prasun Mishra. Now, let me introduce Dr. Prasun Mishra to you all. Dr. Prasun Mishra has been serving as an assistant professor at the Advanced Technology Development Center, ATDC, IIT Kharagpur since October 2021. He received his BTech in Electrical Engineering from the West Bengal University of Technology in 2010, MTech in Mechatronics from the Academy of Scientific and Innovative Research, ACSIR, in 2013, and PhD in Electrical Engineering from the Indian Institute of Technology, Delhi, IIT Delhi, in 2020. He also completed a postdoctoral fellowship at Aalborg University, Denmark during 2020-2021. In addition to his academic career, Dr. Mishra has gained valuable industrial experience. He worked as an assistant system engineer ASE at Tata Consultancy Services, Bangalore in 2010 to 2011, as a quick hire scientist trainee at CSIR CMERI Durgapur from 2013 to 2014, and as a research engineer at GE Global Research Bangalore 2021. He secured second position during his MTech in Mechatronics and received the distinction in doctoral research in electrical engineering in 2020 from IIT Delhi for his outstanding PhD thesis work. Dr. Mishra was honored with the Young Scientist Award for Innovation in Product Design by IIT DM, Jabalpur, Madhya Pradesh, India. He was among the 21 young scientists selected by DST and NIAS India to represent the country at the BRICS Young Scientist Forum and Young Innovation Prize, YSF and YIP 2023, held in South Africa. He was also one of the 3 young scientists invited to the roundtable discussion Young Science Without Borders at the 3rd Science Congress of Young Scientists 2023 in Sochi, Russia. He received the Bengal Excellence Award from the Aranya Bangla Foundation in 2024 in recognition of his inspiring educational journey, starting from a remote village Bengali medium school in East Medanapur to assistant professor at IIT Kharagpur. Indigenous design and development works, multifaceted talents, and their consistent upliftment over time. Dr. Mishra is a senior member of IEEE, IES, IAS, PELS, and a member of the Institution of Engineers India. He has actively contributed to IEEE in various leadership roles, including Educational Activity Chair, IEEE Kharagpur Section, and IEEE Young Professional and Publicity Chair at IEEE ECC Asia 2025 and Intellect 2024. He serves as a reviewer for several IEEE transactions and international conferences with major publications in IEEE transactions on industrial electronics and IEEE transactions on power electronics. He has presented his research in reputed international and national conferences such as PEDES, Intellect, ECC Europe, ECC Asia, EPE, Indicon, and NPEC. Dr. Mishra has also filed multiple Indian and European patents and has been involved in several R&D projects in diverse technical roles. He has developed a new laboratory named as Smart Power Electronics and Electrical Drives Lab at ATDC, IIT Kharagpur, which is known as SPEED Lab. His research interests include advanced power electronic converters and interface circuits, high performance motor drives and control, embedded control systems and real-time implementation. He has delivered numerous invited lectures across India on topics related to power electronics, control systems, and electric drives, contributing to knowledge transfer and skill development initiative. Now, with this introduction, I request sir to address our participants. Over to you, sir.
Okay, so thank you so much for the nice introduction. So I will start my session. So let me share my screen, and I welcome all the participants. And during my session, I will request all of you, please be interactive. Okay, and whenever you need to ask me something, you can stop me and you can ask me. Don't wait for the last moment. Okay, so please cooperate. Can you see my screen? Is it visible?
Yes, sir, it is visible.
Okay, thank you. So yeah, so today I'll be talking about indigenous development of PWM inverter fed induction motor drives and its real-time control with TI microcontroller. Yeah, so she has already introduced myself, so I'll not discuss about that thing, but I will give a brief introduction about Advanced Technology Development Center. So it's a center for doing interdisciplinary academic and research activities in IIT Kharagpur. We do not have any BTech program, but we do have two MTech program. So one is on embedded control and software, so which is recently named as cyber physical system. And we have another MTech program which is on electric transportation. And this program we offer in collaboration with electrical engineering department. We do have some micro specialization course on embedded control and software. We do have so MS by research as well as PhD programs. Although we do not have any BTech program in Advanced Technology Development Center, but many of the faculty member from our center, they offer multiple elective courses, and the students across the institute, UG level, PG level, they used to take our subject as an elective subject. And we do have faculty from various background. We have 3 faculty from electrical engineering background. Then we have faculty from ECE, then computer science, even mathematics, physics, and so on. So let me give you a brief introduction about electrical motor drives. Okay. So if you look at this block diagram representation, you can see there is a source. Okay. So this source might be a AC source, it might be a DC source. Okay. So if I consider it's a grid connected electrical motor drives, right? So either it will be a single phase or it might be a 3-phase. Okay, if it is single phase, then it is 230. In Indian standard, it is 230 volt, 50 hertz. And then if it is a 3-phase, then it will be 415 volt and 50 hertz, and so on. And now, if you consider an let's say some battery operated electric drives, so then in place of source there will be a battery, or if I am talking about, let's say, the hybrid electric vehicle also, so you might have fuel cell and so on. Okay, so this is about the source. And then we also have an electric motor. Okay, so there are different categories of motor: DC motor, AC motor. Okay, so earlier days people used to use DC motor. Even now also they are used for let's say very low power applications. But generally for energy efficient and high power application, and even the low power application also, nowadays people are using brushless DC motor, then permanent magnet synchronous motor, 3-phase induction motor, and switch reactance motor, synchronous reactance motor, and so on. Okay, so there are many two categories. One is non-permanent magnet AC machines and permanent magnet AC machines. So the permanent magnet AC machine, their energy density is in the higher side. Their efficiency is quite good, but as you can understand that it's the performance of the machine, it depends on the properties of the permanent magnet. And sometimes some of the machines has power factor issues, some of the machines has torque ripple issues. Okay, and on the other hand, the induction machine, the technology is quite mature and it is quite rugged. Okay, so you can use for various applications, and it has been used for various applications, starting from EV, and then let's say all the industrial drives, then traction applications, and so on. Okay, and then we basically deploy this. Okay, now we have the source, either it's a AC or DC source, and we have the machine, either it's a DC or AC. So obviously we need a power converter if we want to control the torque and speed of the motor, because finally the shaft of the motor is connected with some mechanical system, so which is represented in this diagram as a mechanical load. Okay, now depending on the application, we have different torque and speed requirements. Okay, so and the electric motor needs to cater to the requirement of load, then only this operation will be successful. Okay, so that is why we need a power converter. And within the power converter, we have a lot of semiconductor switching devices, and we need to control its turn on and turn off operation to generate suitable voltage and current at the motor input terminal, so that the motor can we can run the motor at that particular speed and torque, and also it can provide that much amount of torque to meet the load requirement. And yes, now if we are going for a closed loop control, obviously we need feedback from different sensors. And if I consider a generalized electric motor drives, we put different sensors. Let's say we sense in some of the application, if you are controlling the position also, you need some position sensor. And in some of the application, if you want to control the speed, either you estimate the speed from the position, or you can also deploy the speed sensor also, like encoder and so on. And if you want to control the motor voltage and current also, we generally put some voltage sensor, current sensor at its input terminal. Sometimes we also want to maintain the DC link voltage. Let's say if you have a grid connected drive, so where you have a back-to-back converter, so there will be so in the first stage there will be AC to DC conversion, and then we'll be using a DC to AC inverter. Okay, so in that case, we also sense the grid current, and we also sense the output voltage of the PWM converter, that is the front end converter, to maintain the constant DC bus voltage. Okay, now all these sensor feedback that will go to a motor control unit. So in this motor control unit, we generally use some microcontroller. Okay, so you can think of DSP microcontroller, then FPGA, then TI microcontroller, and so on, ST microcontroller, so on. So it depends on the applications. Okay, so and based on your application requirement, so you'll select your embedded control platform. Okay, and the embedded control platform should have sufficient interface to process multiple sensors, as well as it also has to generate some PWM pulses for the power converter. Okay, and now from the input from the user side, so either you can give you have to provide some reference, that is for the position or the speed or the torque. If you consider an EV application, so your microcontroller uses it interface with some accelerator pedal. Then if you want to stop the vehicle, then obviously there should be some brake signal. Okay, then you might have some command for the forward and reverse. Okay, and obviously there will be multiple sensors, and within this embedded microcontroller, so you will basically implement your motor control algorithm. Okay, and based on your motor control logic, so it will generate some PWM pulses. Okay, now those pulses will go to the input to the gate driver, which is present in the power converter module. And the gate driver will be driving the semiconductor switching devices. Okay, and that is how it will modulate the output voltage and output current of the power converter. So this is a very simple explanation of a generalized electric motor drives, and what are the different applications. So I have listed a few applications. So let's say automobile and EV application, as I have told you, right? So let's say if you consider mainly for the two-wheeler and three-wheeler application, we generally use PMS in, like let's say the BLDC motor. If you look at the drivetrain of electric Toto rickshaw, so they generally use low voltage, high current BLDC motor. So generally their voltage in the range of 48 volt, and the power rating, let's say in between 1.5 kilowatt. So it depends on, so there are the different categories of three-wheeler, let's say passenger, maybe some cargo three-wheeler and so on. So based on the vehicle configuration and also the application, so you'll decide the rating of the motor. But if you consider the EV application, so from the load characteristics point of view, as you can understand, if you think from the wheel side actually, so you have a very dynamic, you needed a very dynamic torque and speed profile, and the motors would have high starting torque. Okay, because when you're accelerating your vehicle, that time your tractive torque requirement is the higher range. But if you are going at a constant speed, that time that requirement will be lower, and the vehicle can run at various speed, right? So the drive has to operate at various operating conditions, and whenever you are applying some brake, so that time you need to apply some negative torque, right? So we need to operate the drive in four quadrant operation, right? So the torque and speed, positive, negative, and multiple combinations as possible. Now, one of the major application is also traction and locomotive applications. Okay, so there also we need very high starting torque, and then there are some other requirements. So there are other application like steel loading mill, paper and textile mills. Okay, so their load characteristics are different. If you consider cement industry, so what will happen actually? So you will have hard rocks, right? And you need to crash those rocks. So here, if you look at the load requirement, so you do not need a constant torque, but you need a intermittent high torque so that you can do the crashing. Okay. Then there are other applications, let's say industrial pump and refrigeration and food processing industry and so on. Okay, so for nowadays, so you will find the BLDC ceiling fan that is also coming. So that is also another applications. Okay, so if yeah, and then if I consider a lift or elevator application, so there you do not have any very high speed requirement, the uh, but the thing is that at zero speed you need to control the torque. Okay, let's say you are in the ground floor, and everyone has entered into the lift. Okay, now the lift has to lift all the passengers from the ground floor to the, let's say, on the seventh floor. Okay, so it needs very high starting torque. At the same time, it needs to control the very low speed, and you have the load torque is quite in the higher range. And there are another application, let's say the wind energy conversion system. So there will be a wind turbine, and then you have either you will be using doubly fed induction generator or maybe the PMSG. So that will generate some power, and then you have a back-to-back converter system by which you will generate power also. So there are some other applications also, household application, then your robotic application. Okay, nowadays in a drone application also, so people are using drives. So from this discussion, it is very much clear that we cannot live we cannot live without drives. Okay, so either it's a small power drive or medium power or low power drive. But in our present day-to-day life, so we are using drive in one way or other way. So I'll just give you some overview of electric transportation and in adaptation. So if you look at the IC engine driven vehicle, so what are the drawbacks it has? So as you can understand, it has tailpipe emission, which is polluting the air, and the propulsion is quite a noisy propulsion. So it is also creating sound pollutions, and we need to import the crude oil from the foreign countries. So that way, it is also dependent on. We also have some dependent on the foreign countries. Its running cost is also in the higher range, and we do not have any recovery scheme for the braking energy. And as you can know that the IC engine, so they don't have the maximum torque capability at the zero speed. Okay, and at the IC engine, and the IC engine, if you look at the torque peak characteristic of the IC engine, so with the help of multi-stage transmission gear system, we are basically realizing a constant power characteristics. So let's say at, at the lower speed you have the high torque, and the more you increase the speed, the torque will be reduced, so the your power will remain constant. And the major drawback is its efficiency is quite poor. So the IC engine efficiency it will be in the range of, let's say, maybe 25 to 35% in that range. Okay, so that is why the whole world actually they are moving towards the electric mobility. Okay, so in the electric mobility there are multiple configuration. It might be a battery operated electric vehicle, or maybe it's an hybrid electric vehicle. Okay, so what are the advantages of EV technology? So you don't have any no tailpipe emissions, and the efficiency of the motor is also in the higher side. So it is more than, let's say, 85%, and people are doing research to increase its efficiency further. And then as the electric motor has flexible torque and speed characteristics, so we do not need multi-stage transmission gear system. Maybe the single stage gear is sufficient enough. And the dynamic characteristics of electric motor is much faster than the IC engine driven vehicle, so the propulsion will be quite faster. And the ride of the electric vehicle, that is quite silent as compared to IC engine driven vehicle. And the beautiful thing is that whenever you are deaccelerating your vehicle, that time you are applying brake, so that time the motor will be acting as a generator, and it can generate some you can basically convert the kinetic energy of the vehicle into electrical energy, and you can store in a battery also, right? So that way you are recovering some of the braking energy. And in case of electric vehicle, actually, so in case of electric motor, so the motor can operate up to the rated speed, but it is also possible to operate the motor beyond its rated speed, but we need to reduce the torque, okay? Because if we are increasing the speed, keeping the torque constant, so obviously the power will increase and we will exceed the rated power condition of the machines. So what we can do, that we can increase the speed and reduce the torque by we can by field weakening operation, and that is how we can realize its extended speed operation, that which is very much required for high speed EV applications. And the maintenance is also quite, also in the lower side. And we can obviously charge the battery from the grid supply, or maybe we might have some different renewable energy sources like, let's say, wind energy, solar, and so on. And whenever you are not using the, let's say, the EV battery, so that time also you can use that battery to feed some power to the grid. Also you can use it for power factor correction and so on. And the electric motor has also the capability of providing maximum torque at zero speed, so which is quite necessary for EV applications. Okay, now I will leave you one point. But so all the people are talking about, let's say, the electric mobility and so on. It is quite a green technology, but is it a green technology? So there is some debate also, right? Let's say if you consider this IC engine driven vehicle, if you consider the wheel to wheel efficiency, okay, so where you are extracting the oil, okay, then you are refining that oil, then you are transporting that oil that is coming into a, let's say, the petrol pump, okay, then from the petrol pump you are taking that oil, then you have the IC engine driven the vehicles, and finally you will calculate the overall efficiency from the wheel to the wheel actually. So you will have some figure. Similarly, if you do the similar calculation for, let's say, for electric mobility, so here I'm considering that, let's say, the battery is battery, you are charging the battery from the available grid power supply. So so you are generating that, let's say, that power somewhere means from a, let's say, from a thermal power station. So you need to consider different stages, right? So you are importing the coal, then you are putting it into a thermal power station, then you are generating some electric power that will be available to your household, means at your home. Then you will be charging your battery, then finally the battery to the motor, and motor to the wheel. Okay, now if you consider this efficiency also, so there is some debate that either EV technology, it's a green technology or not. Okay, and or what are the benefits that you are getting from the EV technology? One benefit that I am quite sure, that if you are using IC engine driven vehicle, so your pollution is discrete. Okay, so you are polluting the environment at very different places, maybe some places where your population density is quite high, but with the help of EV, actually what we are doing, so we have a centralized pollution. So we are shifting all the discrete pollution to one place where maybe the population density is not that much high. And obviously, so if you look at the characteristics of EV, okay, so we have some advantages like it's faster propulsion, and then the braking energy, recovery of braking energy, that is also quite advantageous. Okay, and yes, and then and then the other thing is that that the disposable. So let's say that we are using different electronics components, semiconductor devices, we are using battery and so on, but all these are not biodegradable, right? So finally we need to dump it somewhere. So that is why nowadays the research is going on to recycling different components of different EV components. Okay, so there are different aspects, or from the different angle we can discuss about this EV technology. But one thing is it is also promising that that instead of charging the batteries from the, let's say, the available grid supply, if we can incorporate more renewable energy system actually, so that then it has some advantages. Okay, so I'm not going to that those aspects, but there are some discussion around these IC independent vehicle, electric vehicle, hybrid electric vehicles, because in case of battery operated electric vehicle, the range anxiety, this is the main problem. Because if you look at the energy density of the petrol and energy density of the best battery which is available in the market, so at least 1,000 times higher than the petrol. Okay, and also your the charging time of the battery, that is also quite high as compared to the petrol. Let's say if you go to a petrol pump, let's say within 2-3 minutes you can fill your fuel tank and you can come out. But for if you're using EV, so you need to charge the electric battery, you need to wait for some times. Okay, even if you are using the fast charger and other things. So that is why the battery swapping technology and other things that is coming out, but the technology is not mature enough. Okay, so yes, but still I think it is still promising, but it is still promising if we integrate the different renewable energy sources to charge the battery. If we can find some methodology to dispose all the different electronics and let's say the chemical components of the battery and so on, so that then only it will serve our purpose in the long run. So Indian governments and also in the global level, there are different initiatives that was taken by the Indian governments. There are different schemes like FAME 1, FAME 2, PLI, SEC, battery swapping, and if you are purchasing the EV, so you'll have some tax and duty reduction. Okay. So anyway, so that is all about the electric transportation. And when you are talking about electric transportation, we think it will be on-road vehicle. But apart from on-road vehicle, we have the electric aircrafts, we have the ships, let's say we have the drone also. Okay, so all these are examples of electric transportation. So it has wide applications. Okay, so if I consider an overview of EV drivetrain, as you can see that you can have, along with the battery, you can have a multiple sources like supercapacitor, fuel cell, and so on. And and we have a AC motor, right? For to operate the AC motor actually, so we need a DC to AC converter, and the DC side of the DC to AC converter that has to be fixed. Okay, but but the battery voltage that may reduce over time. Even the fuel cell that you are using, that is not same as the battery voltage. So but we need a common DC bus, right? So that is why we are using a DC converter also. And whenever you are let's say the motor is operating the generating mode, so if we want to do the regenerative braking in a controlled manner, so sometimes having a DC converter is it's a better option. Okay, and sometimes we also use supercapacitor because the power density of supercapacitor is quite high actually. So and so if you consider a battery, so the when you purchase a battery, they always mention a life cycle, right? So how many times you can charge and you can discharge the battery. But if you look at this number for the supercapacitor, it is quite high, right? So you can quickly charge and quickly discharge the supercapacitor multiple times as compared to the battery. So that way supercapacitor is quite advantageous. Let's say when you are accelerating the vehicle, so when you are applying the brake actually, so that time maybe the regenerative energy that you can store in the supercapacitor. And whenever you are accelerating the vehicle, that time you need more power requirement. So some of the power can be shared from the supercapacitor and some of the things will be from the battery, and you might have a coordinated control system and so on. So yes, so this is one example of let's say electric transportation. And there are different power converters, let's say DC AC, AC DC, and DC DC, so on. So there are some other power converter, power electric converters that are used for EV application. Let's say if you have an onboard charger or if you have an offboard charger, so there are let's say wire charging, wireless charging, and so on. Now coming to the electric motor, as I told you that that you might be using BLDC motor, then induction motor, PMSM, IPMSM, then switch reactance motor, synchronous reactance motor, and so on. So they have, all these motor have their own advantages and disadvantages, but we need to select the motor based on our application requirements. Okay, so there you will consider different factors, even the cost also, even the size of the motor, even the efficiency, even the technological maturity, even the availability of different components which are required for motor manufacturing and so on. So there is some other application, let's say for the traction application. So there we generally use a single phase 25 kV 50 hertz system. Then we have two front, and after that there is a transformer. So this transformer has two secondary winding, and each secondary winding is connected with front end converter. So there are two front end converters. They are connected. Their outputs are connected in parallel, so they are generating a DC bus voltage of around 2.8 kV. So this choke is optional. Sometimes they use choke, sometimes they don't use any choke also in the DC link side. Then you have a DC link capacitor, and after that you have the traction inverter, and which is basically running, which is basically feeding the power to a motor. And the rating of the motor is generally 2.18 kV, and its power rating is in the range of, let's say, 850 kilowatt, and the frequency is 0 to 160 hertz. Okay, and sometimes they also use some chopper circuit in the input side of the power inverter, because when you have some regeneration and other things, so that time you might have a overshoot in the DC link. Okay, and we need to dissipate that energy. So as you can see, we have a bleeder resistor there. Okay, and we have a switch there. So whenever you have some overshoot in the DC link side, so that time you will turn on the switch, and then that power will be dissipated in the bleeder resistor. Okay, so this is another configuration where we are using let's say the induction motor drives, or you can also use some PMSM also, but mostly in India, actually electric traction application, people are using induction motor drives. Okay, now I was talking about the four quadrant operation, right? So whenever you are designing, you are using an electric motor, and for different application actually. So if you can design your motor controller to realize the operation of the electric motor in four quadrant, so then it is quite good. Let's say if you consider an EV application, let's say here I'm showing you the speed profile and the torque profile. So let's say you are accelerating the vehicle, right? So your speed will increase. Obviously, if you want to accelerate your vehicle, so you need to apply, so the motor has to deliver positive torque. So that is why you see the torque is positive, and then and the vehicle is going in the forward direction. Okay, now the vehicle is still going in the forward direction, but you want to deaccelerate the vehicle, means you want to reduce the speed. So what you have to do, your speed will remain positive, but your torque has to negative if you want to deaccelerate the vehicle. Now when you have yes, now when you have come here actually, so you have the zero speed, and now what is happening actually, so you are accelerating your vehicle but in the reverse direction. Okay, so in the backward direction. So that time also, as you can see, the your your speed is negative as well as the torque is negative, and then again you are deaccelerating your vehicle. Again you are deaccelerating your vehicle uh, in the in the backward direction. Okay, so that time also again your torque is positive. Okay, now if you relate these two things, right? So sometimes your vehicle is accelerating, sometimes it is deaccelerating in the forward direction or in the reverse direction. So accordingly your torque is positive or negative. Okay, so you can divide all these operations into four quadrant. Okay, so let's say this is in the x-axis you have the speed, in the y-axis the torque. Okay, so if it is in the first quadrant, your speed and torque both are positive, so it is operating the forward motoring mode. Then if it is in the second quadrant, you can see the speed is negative and the torque is positive, so it's in the reverse braking conditions. Okay, and then in the third quadrant, so your speed is also negative and torque is also negative. Okay, so means the vehicle is going in the backward direction, so it's a reverse motoring, and then you to have a forward braking also. Let the speed is positive and your torque is negative, right? So whenever, so this is this zone actually. So when you are, your speed is positive but you are applying some negative torque to deaccelerate the vehicle, so that time this braking operation will happen. So this is the overview of four quadrant operation of electric motor, and I have taken one example of to explain this. I have taken one example of EV. I hope you are able to connect and you are able to understand that how the four quadrant operation are relevant for EV applications. Okay. So now I'll start it. I'll start discussing about the pulse width modulated voltage so inverter fed three-phase squirrel cage induction motor drive. So in the category of induction motor, you have slip ring induction motor, you have squirrel cage induction motor. In case of slip ring induction motor, you have access to the stator terminal as well as the rotor terminal also. But in case of squirrel cage induction motor, you don't have any access to the rotor terminals. You only have the access to the stator terminal. Okay. And I think the basics of the induction motor it was already covered in this particular program by some of the speakers. So I'm not going into the explaining the basic operating principle of induction motor and other things. Okay. So I'll assume that you are already aware of the basic operation of induction motor. Okay. So it is basically an asynchronous motor. It cannot run at synchronous speed. But if it start running at synchronous speed, then what will happen that there will be no flux cutting, and then there will be no torque. Okay. So that is why there will be sleeve in the induction motor. If I take an induction motor, it's a 2.2 kilowatt, let's say 50 hertz 4-pole induction motor. So the synchronous speed will be 1500 RPM. But it's the actual speed of the motor will be, let's say it will be 1485, 1495. Obviously, there should be some sleep. That is called the slip speed. Okay, so your synchronous speed equal to the rotor speed and the slip speed. And okay, so to control the torque and speed of the motor, obviously we need a power converter. Okay, we need a DC to AC converter. Let's say if you assume if you have a constant DC source, let's say you have a three-phase power supply in the lab, then you have a controlled AC to DC power supply which is generating a regulated DC supply, and after that you have a voltage switch inverter which has gate driver circuit, then protection circuit, and lot of interfaces, and the output of that converter is connected to the induction motor, and the motor the shaft of the motor is connected to either to a DC generator, or you may use some dynamometer also for variable loading. Okay. And then obviously if you are doing the closed loop control, you need multiple sensors. Okay. And then you have some you'll give some reference from the user side, and all these things will go to a digital signal controller. So in today's talk I'll be talking about the TI microcontroller. So let's say, so one of the microcontroller, that is TMS320F2835, it belongs to the C2000 series, and it's a Delfino series microcontroller. Okay. And finally, if you'll generate the PWM pulses, that will go to your converter. Okay. So as you can see that here here I am showing you a schematic diagram for a two-level voltage source inverter. Okay. So in the input side you have a constant DC voltage, and in the output side where the voltage is variable voltage. Okay. Now based on the loading condition, the current will also vary. Fine. Now in such converter, actually we generally use different semiconductor switching devices. Okay. So let's say, so in earlier days, even now also for high power application also people are using silicon IGBT. Okay. In some of the application they are using silicon MOSFET. In some of the application they are using silicon carbide or gallium nitride switching devices. They also use some Schottky diode in parallel to the switching devices also. Okay. So yeah, so if you consider a two-level voltage swing inverter, so majorly you will find six MOSFETs or IGBTs, and also you have six Schottky diodes which are connected in parallel uh, uh, with the IGBT or MOSFETs. Okay, now in the DC link side also you have a DC link capacitors. Okay, so sometimes people also use two capacitor connected in series, and also uh, and sometimes they also keep in provision to have the midpoint of the DC link. Okay, now we can also now if we want to design the controller for an let's say this motor die application. So what I do actually, so I I want to have I want to write down all the equations. Okay, all the equations, so that we can mathematically model the overall system, starting from the inverter, then your motor, and so on. Now, how we can do the modeling of this inverter? Okay, so if you consider, let's say, you can see there is one point that is called O point here. Okay, so sometime in some of the books you will find they consider this midpoint of the DC link as a O point. Sometimes they consider negative terminal of the VDC also as a midpoint. Okay, now you have you have three legs, right? And the midpoint of each leg, they are considered a phase point: A phase, B phase, and C phase. Okay, and they are connected with the load. Either it's a star connected load or it's a delta connected load. In this case, it's a star connected induction motor. Okay, now the voltage between this point, A point and O point, this is called the pole voltage. Okay, either you consider the O point here or you can consider O point here. If you consider this O point here, actually, the when you are turning on the switch S1, okay, so that, and obviously the switch S4 will be turned off during that time, because if you turn on S1 and S4 at the same time, what will happen? Your DC link will be shorted, and this phenomenon is called shoot through phenomena. Okay, so at any instant both the switches will not be turned on at the same time. Okay, so you need to ensure that S1 is off, and then you need to turn on S4, or you need to turn off the S4 and then you turn on the S1. Okay, so the gate pulses that you are giving to S1 and S4, they are complementary in nature, and it is true for all the legs also, right? And in ideal case, we are assuming, okay, so when you are turning on the pulse, the switches will be turned on and turned off immediately. But in actual case, so if you are giving a, let's say, if you are applied 20 volt to the gate to source terminal of an MOSFET, actually, the MOSFET will take some finite amount of time to completely turn on. Okay, now during that time, if you also given some turn on pulses to the bottom switch also, so then what will happen actually? So during the switching transition, okay, one switch is turning on slowly and another switch is turning off slowly. So you will have a common point where both the switches will be on. Okay, so, and that will create this shoot through phenomena. So that is why we introduce some dead time in between these two signals, so that we can avoid this shoot through phenomena. Anyway, so I am coming to that modeling part actually. So this is called the pole voltage. Okay, so if you are measuring the phase voltage with respect to this O point, either it is here or here, this is called a pole voltage. If you are considering the midpoint of the DC link, so in that case your VA0 will be plus VDC or minus VDC. When VDC by 2 actually, yes, when you turn on S1, so that time your, if this voltage is VDC, okay, and if I consider the voltage across CD1 and CDC2 is VDC by 2 and VDC by 2, so what will be the phase voltage actually here? So when you turn on S1, this voltage will be plus VDC by 2, and when you turn on S4, then it will be minus VDC by 2. Now you are, if you are considering this O point at the here actually, so in that case your pole voltage will be VDC and 0. Okay, so this is called the pole voltage. Then from the pole voltage actually, so you can also write down the expression for the phase to neutral voltage, because your pole voltage is nothing but, so your phase to neutral voltage means, so what I'm considering here, let's say you have a star connected load here, this is a balanced load, and the star connected load at a neutral point here. Okay, so what will be the phase to neutral voltage? That will be VAN, VBN, VCN. Okay, now I can write this VAN as VA, I can write this VAN as VA0 minus VN0. What is VN0? VN0 is nothing but the summation of VA0 plus VB0 plus VC0 by 3. Okay. Now, if we do this calculation actually, then finally you will arrive into this expression. So your phase voltage VAN, VBN, VCN has the relation with pole voltage VA0, VB0, VC0 in this manner. Okay. And then what will be the line to line voltage? That will be VAN minus VBN, or you can do VA0 minus VB0, VB0 minus VC0. If you do VA0 minus VB0, that will give you VAB. If you do VB0 minus VC0, that will give VBC. And if you do VC0 minus VA0, that will give you VCA. Okay, so so this is how you can do some modeling of the inverter in MATLAB also. Okay, so where you need only, let's say, the three pulses from let's say you need three S1, S3, S5, and then you generate the pole voltage. From the pole voltage, you generate the phase to neutral voltage, and from the phase to neutral voltage, you generate the line voltage. Okay. Obviously, here in this modeling, we did not consider the effect of dead time here. Okay. But in actual case, actually, we put some dead time to prohibit the shoot through phenomena. But because of the dead time also, you will find that you will find some low order harmonics in the in the current profile uh, of the load, and at the same time also it will also reduce the fundamental voltage of the inverter in certain way. Okay. And the more you will increase the dead time, so this fundamental voltage reduction will be more. Okay. And you will come up and you will introduce a lot of let's say low order harmonics, that is in the range of, let's say, 200 or 250 or 300 and so on, low order harmonics. Okay. I'm not talking about the switching harmonics. Obviously there should be some switching harmonics. And coming to the so okay, now how we are doing the switching of these different MOSFETs. So we generally use different PWM scheme. So there are different PWM scheme, let's say sinusoidal pulse width modulation, then your space vectoral pulse width modulation. Then there are a lot of PWM scheme that is called DPWM, discontinuous pulse width modulation. Okay. So in different PWM techniques, so what they are trying to do, so they are trying to improve the DC bus utilization factor. They are trying to reduce the switching losses, or maybe in some of the application, they are trying to reduce the switching harmonics. So based on this factor, there are different PWM scheme, but industry, in most of the industry, so they generally use, let's say, the space vector pulse width modulation, which has a higher DC bus utilization factor as compared to the standard sinusoidal pulse width modulation. So it means that you can go up to the modulation index 1.15, still you not enter into the over modulation zone. Okay. So that is one advantage of space vector pulse width modulation. And how they are realizing these things, if you look at the space vector diagram for the SBPWM actually, so there are a different space vector. Let's say you have three switches here, right? One switch, it will be 1 or 0. So you will have actually 8 total vectors. So out of 8, there will be 6 active, and then other will be 0 vectors. Okay. So how you are applying this vector at different sectors, based on that, that is the beauty of this space vector pulse modulation. And if you compare the sine PWM and the space vector pulse width modulation, you will see that in case of space vector pulse width modulation, we are applying the 0 vectors for equal amount of time, and that is how we are getting the higher DC bus utilization factor. Okay. So there are different way you can implement this space vector pulse width modulation in a TI microcontroller. Okay, so maybe you can take the BS alpha, BS beta, then you calculate the sectors. Then once you are in the sector 1, then you will decide that how we are going to switch between one state to another state. So that is the standard way of implementing the SBPWM. But there is another way, that is called the carrier based SBPWM technique. So there, what we do basically, we generally have 3 reference voltages, right? So from the 3 reference voltage, we generate that which one is the maximum at one instant, and which one has the minimum value at one instant. Then based on this Vmax and Vmin, we are going to generate some offset voltage that will be minus Vmax plus Vmin by 2. And then we'll add this offset with the original reference signals, and then you'll have a modified reference signal, and that modified reference signal will be compared with a carrier signal. Okay. So here the frequency of the reference signal, so that will be, let's say if you're using 50 hertz induction motor, then so its frequency will vary from 0 to 50 hertz. But the carrier signal that you are using for the comparison actually, so that is same as the switching frequency of the inverter in this case. Okay. So that will be a range of 5 kilowatts, 10 kilowatts, 50 kilowatts, 100 kilowatts, and so on. Okay. The logic is that when the magnitude of your reference signal is higher than the carrier signal, you are going to turn on the top switch of the one leg, and when it is the reverse condition, then you are going to turn on the bottom switch of one leg. So this is I just gave you some brief idea about how we do let's say pulse width modulation in case of a 2-level voltage switch inverter. And you can also easily do it in a TI microcontroller, Okay, so it's very easy. So so you can either use some sine function which is available in the let's say the math library of the code composer studio, or maybe you can write a lookup table for the lookup sign table, and from there you can basically access different data points to generate different sign waves and so on. Okay, so maybe if time permits later on we can discuss all these things. Okay, so there are some other technologies. So as I've told you that, let's say so the silicon MOSFETs are used for, let's say, low power and high switching frequency application, and silicon IGBT are used for medium and high power applications where your switching frequency is in the lower side. Okay, but uh, but there is a new technology which is called silicon carbide. Okay, so now if we compare the properties of silicon IGBT and silicon carbide MOSFET, actually, so the silicon carbide has around 3 times higher band gap, so it is around 3.26, where in case of silicon it is 1.12. It has higher dielectric background field, actually, so it is around 10 times, you can see here, and its thermal conductivity is also quite good as compared to silicon technology. Its saturation drift velocity also in the higher range. So because of this property, actually, what is happening, actually, so nowadays we have lot of medium and high voltage silicon carbide MOSFET modules are available, so which has good promising characteristic to replace the power converter technology, existing power converter technology, where people are using silicon IGBTs. Okay, so it has the higher voltage blocking capability, it has higher temperature withstanding capability, because okay, and then the beautiful thing is that these devices has very less switching transition time. Okay, now if we have very lesser switching transition time, obviously what will happen, the switching loss will be reduced. Okay, so the limitation of silicon IGBT, so for medium and hyper application, so the we cannot operate the silicon IGBT at higher switching frequency, but but for the similar application, actually, so we can go for higher switching frequency operation with silicon carbide. Okay, where and obviously our losses will be switching losses will be in the lesser side. Okay, now when you are operating your inverter at higher switching frequency, what will happen, actually, all the switching harmonics will be in the higher range. Okay, now if you are using some magnetics, so what will happen is, if you want to use some filter or anything to filter out all the switching harmonics, so as the switching harmonics is in the higher order, actually, so the size of the magnetics, that will be quite reduced. Okay, so what will happen, actually, effectively the power density that will increase. Okay, and the other thing is that its thermal conductivity is quite good. Okay, so if you consider the same power dissipation, so in case of silicon carbide, so your cooling requirement will be quite lesser. Okay, as compared to silicon IGBT. So you can use some lesser size heat sink, or for cooling application, sometimes we do natural cooling, sometimes we do forced air cooling, sometimes we go for liquid cooling. Okay, in case of liquid cooling, what happens, they have a pump there, you have an inlet and you have an outlet. From the inlet, water or some oil will inject, and it will absorb the heat from the heat sink, and then it will come out from the outlet. Okay, and that liquid will be circulated through the channels of the heat sinks. Okay, so anyway, so overall, so if you are replacing silicon IGBT with silicon carbide MOSFET, actually, so you can realize the converter having higher power density, higher efficiency, because the conduction loss as well as switching loss, that both will be reduced, so your cooling requirement will be reduced. And the other thing, beautiful thing, is that if you are switching your power converter at higher switching frequency, so you can have the controller which is control loop which is having higher bandwidth. It means that you can have a very faster response time. Okay, and also this high switching frequency operation is quite useful if you are using this particular converter for a high speed motor drive application. Let's say the motor is running at 20,000 rpm or maybe 40,000 rpm, in that range. So it means what, so either your number of poles, so in that case, actually, the fundamental frequency of the motor has to be in the higher range. Okay, so now if your fundamental frequency of the motor is in the higher range, obviously you need to operate your converter at higher switching frequency to realize that kind of phenomena. Okay, so I think you got some overview of the silicon carbide as compared to silicon, and there is obviously, so the gallium nitride powered devices are available. So the silicon carbide are most suited for let's say the medium voltage and high voltage applications, whereas these gallium nitride devices are more suited for low voltage applications, let's say below 600 volt and so on. So they have their own application area, and nowadays people are widely using these wide bandgap semiconductor devices in place of silicon technology. And the cost is in the higher side, but I believe that over time, so this cost will be reduced. But the problem with this silicon carbide technology is that as you have reduced the switching transition time, so obviously your dB by dt and di by dt, that will be in the higher range, and also you might encounter some EMI EMC issues also in your power converters. And to mitigate those things, there are different techniques are available. So so either you can use some filter, dB by dt filter in the output of the inverter, or maybe you can with the help of let's say active gate driving techniques, you can play with these dB by dt and di by dt di by dt that the issues that we encounter in silicon carbide technology. Because at higher switching frequency you have a lot of parasitics in your power circuit actually, so they will play an important role. Okay, so let's say if you have a parasitic inductance actually, so that will be multiplied with di by dt, so L di by dt. If you have a parasitic capacitance, so then dB by dt, C dB by dt, and so on, right? So you will have a lot of EMI EMC issues. So so nowadays a lot of research is going on how to reduce all these things. The major takeaway is that if you reduce the switching transition time, so your switching losses will be reduced, but dB by dt and di by dt, that will be in the higher range. Now if you increase the switching transition time, so your switching loss will increase, but dB by dt and di by dt will be the lesser side. So we need to operate this device having the compromise from both the sides. Okay, so that we need to see. Okay, so then I'll talk about some of the in-house design and development and testing of silicon carbide inverter. So I did my work. So I did this work when I was doing my PhD in IIT Delhi. So so this is the inverter that I developed in. I think it is I developed in 2017. Okay. So here I have used silicon carbide MOSFETs. Okay. So the rating of the MOSFET was around 1200 volt, 32 ampere at 100 degrees centigrade. Okay. So these are from I have used discrete SiC MOSFETs. Okay. So I have made it three-phase two-level voltage source inverter. Here you can see. So here I have a vertically mounted heatsink is there, and all the devices are attached with the heatsink with the help of thermal clip here. Okay. And these inverter had basically different circuits. So one is board is called power and sensor circuit, so which is basically this one, this PSC, and the other one is the gate driver and protection circuit. So this is the bottom one, and we have the control interrepresentation signal condition circuit, which is this one actually. And here we have another PCB where we have put different current sensors. Okay, so I have given the specification of the SiC inverter. So the input voltage, so it's a DC to AC. Okay. So, so the DC voltage, it can take up to 600 volt to 800 volt. The output voltage you can vary from 0 to 415 volt. So we have tested this inverter up to 5 kVA, but you can also go beyond that. Okay, and the maximum switching frequency that we have operated this silicon inverter, that is around 50 kilohertz. Okay, the efficiency of the inverter that we got, it is around 98% efficiency. And this inverter has three current sensors, one voltage sensor. So these three current sensors that we have put to measure the line current of the inverters, and and one voltage sensor that we have put to measure the DC bus voltage. Okay, and it has and within this inverter also we have lot of protection circuit, right? So I over current protection, then over voltage protection, the over temperature protection is there, and then the device short circuit protection, and through DSAT pin of the gate driver circuit. Okay, So, and if you hit any of the protection limit actually, so the operation of the inverter, that will be shut down immediately. And we have multiple LEDs here that we put here, so that will indicate, one LED will glow, and that will show you, okay, you have encountered this kind of fault. And we have a reset switch here, push button here. So by pressing this reset switch, you can clear the fault, and again the inverter operation will be resumed. Okay. And all these board are basically, it's a 4-layer PCB that we have used. Okay. And most of the components are SMD component that we have used, especially in the gate driver and protection circuits. Okay. And on the here you can see that we have made also one interface board. Okay, so where we have used an experimental kit, which is TMS 3202835, and we have not developed this board, but we have developed this board, the bigger one actually, which is the interface circuit. So in this interface circuit, we have the interface circuit for multiple number of ADCs, and then we have the provision of driving silicon carbide MOSFETs also through optic fiber communication, as well as you can also drive semicron IGBT based inverter also from this side. Okay, we also have a 2-channel DAC here, so which is useful for various applications. Okay, so this is a general purpose board that we have made, and where we are using TMS 320F2835 TI microcontroller. Okay, so these we have used. So all the motor control algorithms that was implemented in this microcontroller, and all the output of the sensor that was interfaced with this board. Okay, and then we did the coding in Code Composer Studio. So I wrote the embedded C code to implement various motor control algorithms, and then we have generated the PWM pulses from here. So these are called here we have used optical fiber communication. So these are called the transmitter, and we have the receiver in the here actually. Here you can see this is the receiver and this is the transmitter, and we are transmitting these gate signals from through optic fiber communication to reduce the interference and so on. Okay, and then we have so after receiving the pulses here, then we have a deadband generator circuit, analog circuit. So from there we are generating 6 PWM pulses having the date time, and that we are applying to the input to the gate driver. Okay, so then I'll show you. So this is the top view and the bottom view of those the power board. Okay, so and here we have while we are designing the DC bus actually, so we have realized the sandwich bus bar pattern on the PCB itself. Okay, to minimize the loop inductance. Okay, and we have also put some X capacitor, Y capacitor in the DC bus to reduce the switching voltage surges. Okay, and we also put a lot of film capacitor in the DC bus. Okay, so these are different structure, and you can see this is the device that we have used from Cree. So C2M 0080120D SIC MOSFET, and you can see that how we have clamped this discrete device on the heatsink. Okay, so we have the heatsink here, anodized heatsink here. Then we have put one thermal interface material in between the device and the heatsink. This thermal interface material, they are basically thermally conductive, but electrically they are isolated. Okay, and then we have not screwed this device on the surface of the heatsink. Rather, we have used some thermal clip here, by which we have clamped the MOSFET on the heatsink surface. Okay, and this is the power circuit. So some of the schematic here you can see. So we have a lot of film capacity in the DC bus. Okay, this RB is basically the bleeder register here. And as you can see that at the gate to source terminal of the MOSFET, actually we put some RD here. So if you have some residual charge in the gate to source capacitor, actually that will be distributed here. And we have put some back-to-back diode here. So from the gate driver, output of the gate driver, so for this SIC MOSFET to turn on, we need to apply 20 volt, and to turn off, we need to apply -5 volt. but because of some reason, actually, if your applied voltage is more than that also, so we have a back-to-back diode here, so that will limit the voltage also. Okay, and you can see here from the DC bus also we have put some Y capacitor here. So these Y capacitor are in the range of nanofarad, so they have used for voltage surge suppression also. Okay, so anyway, so we have multiple circuits here, so I'm not going to details here. And this is the schematic for the gate driver and protection circuit. So here we have used some optocoupler here. Okay, so ACPL316A, and in front of that we have used one current buffer here. This is IXTN609A. So this optocoupler has the current sourcing and sinking capability of around I think it is 2 ampere, but this particular IC has the current sourcing and sinking capability of around 9 ampere. Okay, and for the 20 volt and minus 5 volt we have used some isolated DC-DC power converter. Okay, so all these are means off the shelf converter module actually. So the input is 5 volt and the output for one converter it is output is 15 volt, and for the another converter it has plus minus 5 volt. So 15 plus 5, so that will give you 20 volt, and a minus 5 volt that we have used for here also. Okay, and we have designed the PCB actually for the gate driver circuit. You can see here. So this is the 5 volt side and the ground, and this is here you have the 20 volt and minus 5 volt. Okay, and we have put some mechanical cutout in between the input side and output side of the gate driver also here, and we are also given this cutout here also for the power supply also. Okay, and while you are selecting this power supply, so there are different information that you need to gather from the data sheets. Okay, so the isolation capacitance, then what is the your isolation voltage and so on. And while you are selecting any gate driver circuit for these applications actually, so you need to see that that what is the isolation voltage in between input and output, what is the CMRR, and then what is the response time of this gate driver. Okay, once you have applied the pulses. Okay, and let's say some of the gate drivers has some DSAT protection, or let's say some mirror clamp protection, but how fast they are. Okay, because if your protection circuit takes longer time to react actually, so by that time your switch will be gone. Okay, so anyway, so I'm not going to depth here, but these are the circuit that we have used. I think you got some overview. And then this is the top view and bottom view of the gate driver and protection circuits. So we have different protections here: daytime protection, then device current protection, and then load over current protection. So these we have realized based on the sensor that we have used, Hall effect sensor that we have used here. The DC link over voltage protection, that was also realized based on the voltage sensor that we have used. Then we have fault detection and display unit here. Then you can manually reset and reset the fault, and you can clear the fault and again resume the operation of the inverter also. Okay, and this is the interface board. Here you can see this is the 28335 experimental kit, and but this interface circuit that we have made, and this is the optical transmitter, and this is the optical receiver, and this is they are connected with the optic fiber cable, and this is how we are transmitting the gate pulses from this board to the gate driver board. Okay, and this board has multiple circuit like an ADC interface circuit, then DAC. It has also debouncing circuit, the optical transmitter receiver, and so on. Okay. Okay. So so this is how we have tested this inverter at with an induction motor load. So we have kept the DC bus voltage at 600 volt and switching frequency of 50 kilohertz. We have used space-based pulse width modulation. Okay, and we have connected an induction motor 5 HP, 415 volt, 7.6 ampere, 50 hertz, and 1440 RPM. And these are some of the test results, as you can see. So in figure A, I am showing in the line-to-line voltage of the inverter. So so the fundamental frequency is 50 hertz, and the switching frequency is 50 kilohertz. And in figure C, actually, I am showing you the drain to source voltage of the lower MOSFET of one leg and the gate to source voltage here. And in figure B, I am showing the line current of the motor also. Then we have done some continuous run test. So let's say we have continued the operation of the inverter with the same induction motor for continuously 90 minutes, and we have monitored the heatsink temperature. So there are some readings here you can see. So in the first case actually, so we kept the motor was drawing around 3.5 ampere RMS current continuously, and we have not used any cooling fan in that case. The ambient temperature around 37 degrees centigrade. The heat sink temperature goes up to 82 degrees centigrade after 90 minutes. And then we did the same test, but in that case we had turned on the cooling fan. Okay, so in that case we found that the heat sink temperature went up to 49 degrees centigrade, and we repeat the same test, but the current has increased from 3.5 ampere to 7.6 ampere RMS, and that time we found the heat sink temperature went up to 68 degrees centigrade. But the device has means quite higher maximum temperature withstanding capability. So so from this test actually we have assured its thermal stability, as well as so what we are trying to convey here actually. So this operation the operation of the inverter is quite thermally reliable. Okay, and it also works for a long time also without any interruption. Yeah, so then I'll talk about yes. Now, as I've told you that if you consider this inverter actually, so if you look at the output side of the inverter also, okay, now you are connecting a motor here, right? So if you look from the stator terminal, stator has the winding and they have the insulations also. Now the stator winding insulation, they have the withstanding capability of high dB by dt. There is some limit also, okay? So now if we are directly applying the inverter voltage to the motor actually, so what is happening actually? So in the motor input terminals, you will have high dB by dt, right? And that may create some bearing current or maybe some ground current also in the motor. At the same time, so the inverter voltage, it contains the fundamental frequency component as well as switching frequency component also. Okay, and that will increase the core loss inside the machine, right? So one is that how we can reduce the core loss of the machine, that is one thing, and how we can reduce the voltage trace at the motor terminals, so that we can improve the life of the motor, we can avoid its bearing failure and so on. So so what we can do actually, we can put a filter in front of this inverter. So it might be a sinusoidal LC filter, or it might be a dB/dt filter. But here in this case, we have used a sinusoidal LC filter. Okay, so it's a second order LC filter. Here you can see that we are connecting a series inductor, and in parallel we have three capacitors. Okay, fine. Now now if we go for the standard sinusoidal LC filter design actually, so so how do we select the value of filter inductor, and how do we select the value of filter capacitor? So the standard way of selecting the filter inductor is that we need to that we 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 have to specify that what is the ripple in the inverter current. Okay, so that is one thing, and the other thing also is that the voltage drop across the inductor. Okay, these are two factors based on which we select the value of the filter inductor. And we know the switching frequency. Okay, and we also know the fundamental maximum operating frequency of the motor. I'm talking about the fundamental frequency, right? So if you, let's say if your switching frequency is let's say it is let's say it is F switch, and your, let's say the fundamental frequency of the motor is it's, let's say it is F. So you can put the resonant frequency of the filter within the range of 10 times of the fundamental frequency to the F switch by 3 or F switch by 10 also. So so based on the switching frequency and as well as the maximum operating frequency of the motor, you will decide that what will be the resonant frequency of the LC filter. Okay, and from the current ripple as well as from the voltage drop, so you have find out the value of LF. Okay, and you also know the resonant frequency. So resonant frequency is basically 1 by 2 pi root LC. So from that you can find out the value of C. So this is the standard way of, so here I have explained here. Okay, but while you are calculating this L equivalent, you also need to consider the leakage inductance of the machines also, right? Because that will be also coming into the picture. Okay, so this is how we will calculate the L equivalent, and this is the expression of the resonant frequency. So here this LLS and LLR, these are stator leakage inductance and the rotor leakage inductance of the induction motor, and this LF is the the inductance of the filter. Okay, and this is how we will find out the L equivalent. This is the Thevenin equivalent circuit. Okay, and this is the resonant frequency expression. Okay, and this is how we do the design, right? As I've told you that the voltage drop as well as the ripple. Okay, from that you will find out LF, and then you have specify here that what should be the resonant frequency, and from there you can calculate the CF. Okay, but the beautiful thing is that this induction motor, it's a but this induction motor, it's a lagging power factor load. Okay, it's a lagging power factor load, means it, if you segregate this the motor current actually, so it has one active power component of current and another one is the reactive power component of current. Okay, now let's say you don't have any LC filter here, so what will happen? So the active power component of current as well as reactive power component of current, both will be drawn from this side actually. Okay, and both the current that will flow through these inverter switches. Okay, now so what I did actually, so as we are using a LC filter here and we have some filter capacitor here, so why don't you supply the reactive power component of current from this filter capacitor to the motor? So in that case, what will happen actually, the only the active power component of current that will be drawn from this side. Okay, so that way actually you'll find that the current which is flowing through the switches, that will be reduced, and at the same time you'll see the ripple current on the DC-link capacitor, that will be also reduced, and there are some other advantages. So how we have selected the value of filter capacitance, so that has been explained here actually. So if you compare the proposed method and the standard method, so the LF selection value, that is common for both the methods, but while you are calculating the filter capacitance, so in that case we are considering the reactive power demand of the machines. Okay, as you know that when you are running the machine at the no load condition, their power factor is very poor, but if you when you are running the machine in a full load condition, their power factor is quite good. Okay, so this and fine. So now, so what will happen if we can supply the reactive power demand of the induction motor from the filter capacitor? So what will happen, this filter capacitor will serve two purposes. One is that it will attenuate all the higher order switching harmonics, and it will give you a clean sinusoidal voltage waveform at the motor terminal. At the same time, it will also supply some amount of reactive power also. Okay, so this is the final structure. Here you can see that we have the inverter here, we have the control board here, we have the filter capacitor here. So here I have used toroidal iron core inductor, these are the capacitors. But the thing is that in the proposed case, so the size of the filter will be in the higher range. Okay, so here I have given you some calculations. So let's say the fundamental frequency that was considered at 50 hertz, the switching frequency 50 kilohertz. Okay, so in case of standard method, resonant frequencies, it is around 4196 hertz, but in the proposed method it is around 742 hertz. Okay, and the filter inductor value, they are same for both the methods, but in case of standard filter, the size of the filter capacity 1.25 microfarad. For in case of proposed filter, it is around 40 microfarad. So it is obvious that in the proposed filter design method, the size of filter capacitor that has increased, but but we have some advantages. Okay, so this is figure A. So this is the inverter, this is the motor input voltage without any filter, and in the figure B, this is the inverter output voltage and the filter output voltage. Okay, and figure C is the inverter output voltage and the filter output voltage in the proposed case. Okay, so as I've told you that in the first case it is without any filter, and the figure V is here we have the filter, but that filter was designed by the standard method. And in the in the C case, actually this is with the proposed filter method. Okay, as you can see, the motor current are same in both the cases, but you can see the inverter current has been reduced because this filter capacity is supplying the reactive power to the motor. Okay, so this is the top figures are for the light load condition, and the bottom figure is for the full load condition. So obviously, so in the light load condition you will get the benefit, but in the full load condition you will not get that much benefit here. Okay, so there are some table I have put here. You can see the values and other things. Okay, and so here what we have done actually, so as you are applying the sinusoidal voltage and the motor terminals, So how it has some impact on the flux profile of the motor also. That we have investigated here. So you can see in the proposed filter. So in case in the drive having the proposed filter, actually, so the flux profile is less distorted as compared to the standard filter design method also. Yeah. And here I have estimated the DC link capacitor current, means so the high frequency ripple current that is flowing to a DC link capacitor. So the top figure is for the standard filter design method, and the bottom one is the for the proposed filter design method. As you can see that the ripple current through the DC link capacitor that has been reduced here. So if you can reduce the ripple current in the DC link capacitor, so what will happen actually? So you can improve the life of the DC link capacitor, because all these high frequency ripple current, so so that will be multiplied with your the ESR of the capacitor, and it will create some power loss, and that will ultimately increase the core temperature of the capacitor also. Okay. Or you can say that you can select some DC link capacitor in the proposed case having lower ripple handling current capability. Okay. So so the conclusion is that, so in the proposed method, as you can see, the inverter current that has been reduced, so that will reduce the conduction loss in the inverter. At the same time, we have the flux profile of the motor that has been improved. Okay. And also other thing is that the ripple current in the DC link capacitor that has been reduced here. But obviously the size of the filter, LC filter, actually that has the filter actually that has increased, but the size of the inductor that remains same. Okay. And this configuration is more suited for, so I'll suggest that it is more suited for constant speed variable load applications. Okay. Because when we have selected the value of filter capacitor actually here, so here we have considered this Fs, right? So here we have considered Fs equal to 50 hertz. Now if you now if you are using this filter for variable frequency application, this Fs will change, right? So it may happen, let's say the filter capacity that we have chosen, in some cases it will let's say overcompensate the reactive power, in some cases it will undercompensate. Okay. So that is why this configuration is most suited for constant speed and variable load applications. Yeah. And we have published one, I published one transaction paper on this site. So this is quite highly cited papers in IEEE transaction of industrial electronics. Okay. And then I'll talk about the rotor flux oriented control of induction motor. Okay. So if you can understand the control of a DC machine, right? So the torque equation of the DC machine is it's a function of field current as well as armature current, right? And if we consider a separately excited DC machines, so we can control the armature current and field current separately, right? So, and they are decoupled in nature. If I am considering a separately excited DC machines, and in case of DC machines also, so because of the armature reaction, what happened, that magnetic neutral axis that also getting shifted. Okay. So we use some compensating winding in the DC machines to overcome that phenomena. Okay. So what you want, that these two axes, they should be orthogonal to each other. Okay. Okay, so that should be orthogonal to each other. Okay. So so in case of DC machine actually, so now when you are realizing the rotor flux oriented control of induction machine, so we are trying to operate the machine in such a way that the D axis component of stator current and Q axis component of stator current, so they will be orthogonal to each other, and they will be decoupled in nature. Okay. They will be decoupled in nature. Now there are means why you are going for this vector control or field oriented control of induction motor. So in case of induction motor, you have the scalar control, right? So what we do in case of open loop VIA control, so we generally give the frequency reference, and we know the V by A ratio to maintain the flux constant in the machines. And once you know the frequency reference, then from there you can generate that what will be the voltage reference, and from this voltage reference and the frequency reference, okay, so you can generate three voltage reference signals, and then you will do the PWMs to switch the inverter, and based on that your inverter will generate output voltage. Okay. So here actually what you are doing, if you increase the frequency, you are also increasing the voltage. If you reduce the frequency, you are also reducing the voltage, so that you want to keep the V by A ratio constant at all the operating points. Okay, so that is the concept of open loop scalar control, where you don't have any feedback. There is one control technique that is called closed loop VIO control. Okay, so here actually what you are doing, so here you are taking the speed feedback, and there will be a PI controller. You have the reference speed and you have the actual speed. Then you will put a PI controller in front of that. Now that PI controller will generate some sleep speed. Okay, now you will be adding the sleep speed with the actual speed of the motor to generate the synchronous speed, that is the omega s. Okay, now once you have that omega s, then again you will do the VYF control that we did in case of the open loop VYF control. Okay, in a similar manner, but in the first case actually, so when you are not sensing in the speed, okay, let's say the motor is running at a particular operating speed. Now the moment you will start applying, either you increase or decrease the load, actually that time you'll see the motor speed will come down because the sleep will increase. But in the second case, as you are maintaining the as you are taking the speed feedback, okay, now the PI control will try to adjust the sleep speed, and you will see that irrespective of the load variation, so your speed will be quite regulated. Okay, but in this case we are not controlling the current. Okay, so that is why the dynamics of the closed loop VI control is slower as compared to the field oriented control. Okay, so anyway, so to realize the field oriented control, so what we do basically, we do first of all we do the mathematical modeling of induction motor in stationary reference frame, that is alpha beta domain. Okay, and then we convert those alpha beta into DQ reference frame. Okay, why we are converting into DQ reference frame? Because if you're see, if you look at the alpha and beta component of voltage and current, they are sinusoidal in nature. Okay, now when you're uh, now if you are putting a PI controller, okay, the PI controller that will not be suitable for for the sinusoidal inputs actually, because the gain of the gain of the controller means has to be infinite at the desired frequency. Okay, so so if you consider the transfer function of a PI controller, what is that? Kp plus Ki by S, right? Now when your omega is zero, what is S? S is basically J into omega, and what is omega? Omega equal to 2 pi into F, right? Now when your frequency is zero, means it's DC signal, so that time the gain will be infinite, and then only your steady state error will be zero. But if you are putting a sinusoidal input to the PI controller, then you will find that the gain will not be the gain will not be infinite at that at that frequency. Okay, and you will have the steady state error also. Okay, so in case of sinusoidal signal, sometimes people also use PR controller, but the PR controller is more suited for grid connected applications, because for motor drive application, as you know, the your fundamental frequency of the motor that is varying, because you want to operate the motor at a variable speed applications, right? But in case of grid connected converter application, their frequency is more or less fixed. It is very close to the 50 hertz. So this PI controller are more suitable for grid connected applications, but for motor drive application, the PI control is more suited. But nowadays also, so if you want to if you want to use PI controller for drive application also, in that case what you have to do, so in the expression of the PR controller, there is a term called of omega actually. So that omega you need to update online, then only it will give you favorable performance. Anyway, so so as I've told you that you have a three-phase quantity, then you have converted into ABC to alpha beta domain, then alpha beta to DQ. Okay, now while you are converting that alpha beta to DQ actually, so you need one information that is called the omega. Okay, so you need to find out cos theta and sin theta, and then this cos theta sin theta that you will generate based on that omega. Okay, now if you convert the alpha beta quantity into a DQ domain, you will find that these two quantity will be the DC quantity. So D and Q, they will be DC quantity. Okay, so in case of vector control, what you are doing actually, so all the current or voltage that you are sensing actually is all they are AC quantity, the three-phase quantity. But after sensing all the signals within the microcontroller or within the motor control algorithm, we are doing two conversion. One is ABC to alpha beta conversion, then alpha beta to DQ conversion. The moment it has converted into DQ reference frame actually, so all these quantity will be the DC quantity. Then you will be using PI controller to generate the voltage reference, so on, and finally
the output of the PI controller, it will generate some reference voltage that will be VD and VQ. Then again you will do the reverse conversion, okay, reverse transformation, DQ to alpha beta and alpha beta to ABC, okay. And when you have generated the three-phase voltage reference waveform, then you will compare, you will do the PWM technique, sine PWM or space vector pulse modulation to generate the pulses, and that will go to the inverter, okay. So if you look at this diagram, actually here you can see that your the A phase of the stator axis, that is aligned with alpha axis, and alpha and beta, they are orthogonal to each other, okay. And in rotor flux oriented control, actually what we are trying to do, we are trying to align the rotor flux with the D axis of the DQ reference frame. Now here I like to mention one thing. In many of the books, actually, so they are following different convention. In some of the books you will find that the beta is leading alpha. In some of the books they will find the alpha is leading beta. In some of the books you'll find that the q axis is leading d axis, or d axis is leading q axis, okay. In some of the book you'll also find that they are aligning the rotor flux with the q axis of the dq reference frame, okay. Whereas that will create confusion, okay. So you need to follow one convention. So in this work, actually I have followed the convention which is present in the world lunar blue, actually. So that I have followed throughout my work, okay. So here what we are doing, actually, so we are aligning the rotor flux with the d axis of the dq reference frame. And if you do so, this higher phasor, actually it has two components, one is higher d and a higher q. The moment you have aligned the rotor flux, the d axis of the dq reference frame, to the higher q component, that will be 0, okay. Now if you look at the torque expression of the induction motor, actually the moment you will align this rotor flux the dx to the dq reference frame, then you will see that the torque producing component of current, that is isq, and the flux producing component of current, that is imr, they will be so the torque equation that will get, actually it will be a function of isq and imr, okay. So this is very similar to the torque equation of a separately excited fully compensated dc motor, where you can correlate this imr is basically the fictitious magnetizing current, or it is if you multiply this imr with the magnetizing inductance of the machine also, that will give you psi r, okay. So this is basically equivalent to the field current of the dc machine, and this isq is basically the torque producing component of current, which is very which is analogous to the armature current of a dc machines, okay. So anyway, so once you know once you have done the modeling of the machine in alpha beta reference frame, then you do the transformation, you convert all the variables from alpha beta, vs alpha, vs beta, is alpha, is beta, to vsd, vsq, isd, isq, through alpha beta dq transformation. Then you will have these 5 equations, okay. So another one is, the first one is the vsd, okay. You can see this is the vsd is basically the d axis component of stator voltage, okay. So, and so what are the variables are involved in this equation? You have isd, isq, and imr. In the equation of VSQ, you have the contribution from ISQ, then your ISD and IMR. Now you see a very important thing in the D-axis voltage of stator equation. Along with the ISD, you also have some term which is related to ISQ. Similarly, in the Q-axis stator voltage equation, you have some term related to ISD also. It means they are coupled in nature, right? They are coupled, but we want a decoupled control. So that is why what we do, actually. So we'll take out few terms from this voltage equation, and those terms we'll consider as a feed forward term, and we'll add these feed forward terms with the voltage reference of the PR controller. Okay, so these terms are present in the plant, and we are feeding it forward from the controller side. So what will happen, actually, they will cancel out each other, and you can realize a decoupled control. Okay. And this rotor flux oriented control, there are two techniques. One is this indirect IRFOC, and then direct field oriented control. So it depends on how we are estimating the theta. Okay, so here I am talking about it's an indirect field oriented control. Okay, so if I look at the diagram, actually, so I'll show you the control block diagram. So here are basically 4 PR controllers there, and in the outer loop, actually, so we are controlling the fictitious magnetizing current, that is also equivalent to the rotor flux, and also the electrical speed of the rotor. In the inner loop, we are controlling the d-axis component of stator current and q-axis component of stator current. Okay, so we have basically 4 PR controller. So that is named as PCMRS, then PCDS, PCQS, and PCWS. And I have given the transfer function of all these PR controller in the S domain. Okay, and as I've told you that to realize the decoupled control actually, so we are adding some feed forward term. As you can, this is VA wave D and VA wave Q that is being added with the voltage reference, so that they will cancel out each other. Okay. Now, so in case of rotor flux only control, what we are doing here actually, so we are sensing the motor current first. Okay, then we'll convert this 3-phase current into alpha beta, IS alpha, IS beta. Then from IS alpha, IS beta, we need to generate ISD and ISQ. But while you are doing this alpha beta DQ conversion, we need cos theta and sin theta. How we are generating the theta? We are generating the theta by integrating omega mr. What is omega mr? Omega mr is nothing but the electrical speed of the rotor plus the slip speed. And how we are estimating the slip speed? We are estimating the slip speed from this equation. Here you can see this omega, that is a slip speed, that is equal to ISQ by IMR into TR. Okay, where TR is the rotor time constant. Fine. And how do you estimate IMR? IMR you can estimate from ISD by following these equations. Okay, so I hope this is clear. And okay, so once you have ISD and ISQ, so what you'll do actually, so you'll give some IMR reference here, and you have already estimate IMR from ISD. So IMR reference and IMR, that will be compare here. The error will fit to a PI controller. Now this PI controller generate ISD reference. It will be compared with the actual ISD that you have generated from the C-phase current waveforms. And then you have a PI controller here that will generate the VSD star. And we are adding the feed forward term. Finally, this is the final VSD term. And same thing you are also doing in this loop also. So here you have the reference speed, here you have the actual speed, then you are generating ISQ reference from the speed PI controller, and then you are comparing this ISQ reference with the actual ISQ, you are generating some error. Then again you have a PI controller here, it will generate a VSQ star. Okay, and then you are adding the feed forward term. Okay, and finally you have the final VSQ star. And VSD, and from VSD star and VSQ star, you are generating VSS star, VSB star, and VSC star. What you are doing, DQ to alpha beta, then alpha beta to ABC conversion. Here also you need the cos rho MR and sin rho MR, so that you are generating from omega MR. Okay. So now here you can see that here we are sensing the speed. But there are certain applications. So let's say your motor is far away from the power converter. Let's say you are using this motor for oil extracting application, right? So your power converter and everything on the it is on the ship, and your motor is let's say if, it is below the means very far away from the power converter, right? Now if you are using some encoder to sense the speed, and that has to travel a long distance from the motor to the power converter, so in many cases it may happen that the signal will be corrupted. Okay, so that is why in many of the applications, so they don't want to sense the speed, but you need some speed feedback. So how so in that case, what is the way? So you need to estimate the speed. So how you can estimate the speed? You can sense the motor voltage as well as motor current, and from the motor voltage and motor current you can estimate the stator flux, and after that you can estimate the rotor flux, and from the rotor flux you can basically estimate omega mr. Okay, and you have already estimated the slip speed from IMR and ISQ, and you just subtract the slip speed from the omega mr, that will give you the rotor speed. So this is how you can estimate the speed of the motor. See, I'm not explaining all these equation in details because I hope it was covered in the by someone in his previous lecture actually. Okay, so then the question is that how you can design this PI controller, right? So I have seen that many of the students, they try some iterative methods. Okay, so they will put some value, they will see, okay, it is working or not. Okay, it is not okay, they will change some value, right? But if you follow a standard method to find out the value of this KPK of this PI controller, then it is quite good. You can make a small MATLAB script Okay, so just change the parameters in front of the script, and then you'll get all the kpk value. But how you can do that thing? So let's say, so when you are designing the PI controller for the inner current loop, so what we are trying to do, let's say you have the ISD star and ISQ star, and this is the PI controller, transfer function of the PI controller, and this is the transfer function for the inverter actually. So here we are, as we are basically writing down the transfer function of the inverter as a first order delay. Okay, and this delay is happening because, let's say you are doing the closed loop control, right? You have sent some quantity. Now that signal will come to your microcontroller. Now all the sensor interface circuit has some delay, right? Because it has some processing delay. Then your microcontroller also has some processing delay, right? It will do a analog to digital conversion. Then your code will be executed, right? And once you have generated the signals from the microcontroller, now that will go to the gate driver. Then gate driver also has some processing delay, right? And finally the voltage, the signal will be applied to the gate to source terminal, right? Now if you add all the delays actually, so that delay has been represented here in the transfer function of the inverter. So here I have mentioned the transfer function that I have considered for the inverter, 1 by 1 plus STD. So if your switching frequency is much higher, so you can ignore the dynamics of the inverter and you can consider it as 1. But if your switching frequency is lower, it's, let's say it is 2 kilowatts or maybe below 1 kilowatts, then you need to consider this transfer function while you are designing the controller. Okay, so here I'm showing you the block diagram of this controller, and here I have mentioned all the transfer function, right? Now how we can find out now what is my objective? Here you can see the transfer function of PI controller that I have written as KISX into 1 plus STISX by STISX. Okay, so what is KP here? KP is basically KISX, and what is KI here? KI is basically KISX by TISX. Okay, and our objective is to find out what will be the KISX and what will be the TISX. Okay, so what we can do actually, so you can see here we have a 0 in the PI controller here, that is 1 plus STX here. And if you look at the planned transfer function, this is PSD. This is basically 1 by RS plus S sigma LS. This sigma is called the leakage factor. This RH is called per phase stator resistance, and this LS is called per phase stator inductance. Okay. So now what we can do actually? So if we can cancel out these two terms, right? RS plus S sigma LS and 1 plus S TIX. Okay, so from that actually, so we can find out the value of TISX. Okay, so what we can assume that here, so if you assume that TISX equal to sigma LS by RS, then we can cancel out this term and this term. Okay, so these two terms have been cancelled out by assuming TISX equal to sigma LS by RS. Now our the rest of the job is to how we can find out the value of KISX. Now if you do this pole zero cancellations actually, then you need to write down its closed loop transfer function. What will be that? That is basically ISX by ISX star. Okay, so this transfer function will look like this. Now if you, so this transfer function, the structure of the transfer function is very similar to a second order system. That is omega n ISX square by S square plus 2 zeta omega ns plus omega n square, right? Okay, now if you relate these two equations actually, so from this if you relate these two equations, so what is omega n here? Omega n is this one. Then what is zeta here? Okay, now the controller designer, he will specify that what should be the value of zeta. Okay, so for critical damping, basically we consider zeta equal to 1 by root 2 or 0.707. If you are overdamped system, you increase the value of zeta. If you need a little bit underdamped system, reduce the value of zeta. Okay, so you from the design criteria, you select the value of zeta, and from there actually you can find out the value of KISX. Okay, so you got the expression of TISX, which is sigma LS by RS. Here you can see all these are motor parameters, and by doing the no load test and block load test of the induction motor, you can find out all these parameters. Okay, now this KISX also you can see the zeta SX that you have decided. The TISX, this is basically the that you already know. RS also you know, and this TD is basically the delay in the inverter also. Now if you are not considering this transfer function, then you will see that this this closed loop transfer function, it will look like a first order system also. Then your job is, your life is more easier. Okay, so this is how you will find out the value of kpki, and you can also calculate the what will be the bandwidth of this control loop also. That also you can calculate here. Okay, now so the same approach you will follow for DXC and QXC current controller. Okay, now how you can design the kpki value for this IMR and as well as this speed also, right? This IMR and speed also. Okay, so for that actually, so what you have to do, so you need to approximate this transfer loop transfer function. So from the second order system to, you need to approximate the first order system, the ISD star by ISD. Then you have this transfer function from ISD to IMR. Okay, then again you follow the same methods to find out the value of this kp and ki of this IMR. Okay, so here I have given the expression, and yeah, so this is the methods that you can follow here. Fine. And then coming to the speed control actually, so in case of here, in case of IMR control actually, so here you are approximating the closed loop transfer function of ISD by ISD star. Similarly, for the speed control, you need to approximate the approximate a first order transfer function for ISQ by ISQ star, and this is your control loop diagram. So here basically we use symmetric optimum method, because if you look at the open loop transfer function of this control loop, you'll see that you have a double pole at the origin, and if you draw the Bode plot, you'll see that the initial slope will be minus 40 dB per decade, and also the initial phase will be around minus 180 degree. Okay, but for the grain crossover frequency to occur at the slope of minus 20 dB per decade actually, so what we'll do, we introduce some zero here. Okay, so this method is called symmetric optimum method. So by following this method, you can find out the value of kW and tW. So this is basically the parameter of this PI controller. Here you can see that we have used a low pass filter in the speed feedback loop also. This TF is nothing but the time constant of that filter. Okay, so this is, so here I have taken some parameters, and so here I have used one 2.2 kilowatt motor, and these are the motor parameters, and these are the calculated value of kpki. These are the bandwidth. So here the switching frequency, it is 5 kilohertz here, and the bandwidth of the inner loop is 375 hertz, this one 85, and the speed loop is 5 hertz, because the speed loop loop control bandwidth will be quite lower. Okay, now if you do the simulation, you can see here. So here what we are doing, we have given a speed reference of 300 radian per second, and so what we have done here actually, so initially we have settled down the flux. Once the actual IMR has reached around 90% of the reference value, then we have started the speed loop. Okay, and as you can see that, so here at this point at 2.5 second we have applied the load, and at 3.5 second we have removed the load, and you can see the good tracking performance. The actual speed of the motor is tracking the reference speed, and also this IMR reference and IMR, they are also following each other, and the current is also quite good. So this is for the rated speed and with and without load application, and this is at the low speed applications. Okay, so here we have given a speed of 100 radian, and here we have applied the load, here you have removed the load. You can see the current has increased and decreased, and everything is fine. Okay, but here we are doing the control of SQM drive without any filter. Okay, now so what you have understood, that the rotor flux unit control of SQM drive, it's a stable drive, but the moment we'll introduce a filter in between the inverter and the motor, so the dynamics of the filter, it is going to affect the closed loop dynamics of the drive. Okay, and this is the modeling of so now if you include if you write down the dynamic equation of LC filter in the DQ domain, actually you have these equations. Now if you incorporate this equation with the motor actually, so and then if you do some small signal analysis, so you can represent all the equation in the state space. Okay, so you can write down all the state space equation by adapting small signal analysis, and here we have done the small signal analysis of SQM drive with filter. Okay, fine. Now if you do certain analysis, okay, so if from this state space representation, you can write down the transfer function, right? ISD by V inverter D, ISQ by V inverter Q, and now what will happen actually, so this PI controller, that will remain same. you have the inverter transfer function, but now this PSX that has been changed. Now initially this PSX was only the motor transfer function, but now it includes motor as well as filter also. Okay, now if you do not change the value of kpki, and if we plot its closed loop 0 and poles, you'll see that at certain frequency you will have some poles in the right half of S plane, and because of that, and if you investigate the location of the poles, you will see the location of the poles is exactly at the resonant frequency of the filter. Okay, so what is happening actually, because of the resonance phenomena which is happening in the filter, so that is basically affecting the closed loop dynamics of the existing vector control drives, and you will find that at various operating point, so your drive will be unstable, and that that can be guaranteed from these waveforms. You can see that, you can see the stator current and stator voltage profile here. You see you have lot of oscillations at, this is at 200 rate per second. You have a lot of oscillations, and if you calculate the frequency of this oscillation, this is same as the resonant frequency of the filter, and that also has been validated in the pole zero plot. Okay, so now how we can damp out these oscillations in the stator current and stator current actually. Okay, so what you can do, we can put some passive damping resistors also in series with the inductor or series with the capacitor or in parallel with the capacitor also, but that is a lossy techniques. So that is why what we are trying to do, we are trying to damp out this filter resonant frequency oscillation through active damping technique without incurring any losses. Okay, so for that actually what we are doing actually, so the basic structure of the RFOC that will remain same. Okay, so we are adding some extra compensating term that I have indicated here, but how we are generating this compensating term, so what we are doing actually, so if you look at the inverter current, okay, now this inverter current, it contains the motor current as well as the current which is flowing through the filter capacitor, that is the resonant frequency component of current. Okay, so what we did actually, so we have changed the inverter current, then we have converted it into DQ domain. Okay, then we have put a low pass filter here. The frequency of the low pass filter is same as the your so it is same as the resonant frequency. So what we are trying to do actually, so so from this inverter D and inverter Q, we are trying to extract the resonant frequency component which is present in the inverter current. Then we are multiplying with some gain to generate this compensating term. Okay, so here you can say, see, and here one thing I need to say, that my ADC sampling frequency and switching frequency, they are same. Okay, so in this, so in the extracted high frequency component of D axis Q axis, no switching frequency component will be present, because if that is present, then we will be violating the Nyquist sampling criteria. Okay, so we have found that all the high frequency components which are present in these two terms, actually they are basically the filter resonant frequency component, and then we are adding some gain and we are adding with these things. And then if you do so, and how this term has been reflected in the state space equation, here you can see after adding these two terms has been added here actually. Okay, these two diagonally they have added, and now if I again write down the transfer function, and again if I do the pole zero map actually, so you see the right up pole actually that has been shifted from right hand side to the left hand side. Okay, and you can see the initial oscillation which was there in the ISA and this waveform, so that has been damped out, and you have a clean waveform of stator current and stator voltage. Okay, so through active damping technique, we are shifting the pole, okay, from right hand side to the left hand side of the S plane. Okay, but how far we should shift the pole? Okay, but that depends on the value of this K damp, how we are selecting the damping gain. So to find out that actually, so what we have done, so we have done some analysis at different operating points. So we are varying the damping gain iteratively, and then we found that when these poles are locating in the imaginary axis of the S plane, so that we have considered the critical value. Okay, so in different operating points, at least the selective value of K damp has to be higher than this one. Then only you have this clean waveform. At the critical point, you have this kind of waveforms. Okay. So yeah, so this is the things you can see that here. So from 0 to 2.5 seconds. So we are running the rotor flux oriented control of induction motor with active damping technique, and at 2.5 seconds we have removed the active damping technique, and you can see that you have a lot of oscillations in the motor current and the motor voltage, and your system will be unstable at this operating point. Okay, and these are zoomed version of waveforms. Okay, and these are done at different speed. So here we have shown you the operation of the drive with active damping technique. Here we are applying the load, here we are removing the load, everything is fine. Okay, so this is fine. Then we have also validated in the experiment also. So this is one steady state waveform of motor voltage and motor current without active damping technique and with active damping technique. You can see the difference, that all the resonant frequency component that has been damped out actively, and you have a clean waveform here. So this is a 200 radian per second, and we have also taken this waveform from the oscilloscope, and then we have done the effect analysis also, just to show that what was the frequency of these oscillations in the real setup. You can see that, you can look at this component, so that this 516 has component of 600 volt, and it has been attenuated to around 1. It is very low, 0.5 volt and so on. And similar thing has also happened with the current waveform also. So these two waveforms are without active damping technique, and these two waveforms are with active damping technique. And similarly, we have done we have collected waveforms for other operating point, let's say 100 radian per second, 250 radian per second, and so on, just to validate these phenomena. Okay, and then we have validated dynamic performance of the drive with active damping technique. Here you can see that we are increasing the speed of the motor gradually from 32 radian per second to 150 radian per second, then 300 radian per second. And we have plotted the stator current and stator voltage waveforms. Okay, so here we are validating drive at let's say the motor is running at 100 radian per second. Here we are applying the load, here we are removing the load, and here we are showing the zoomed waveforms. All these are with active damping techniques. And this is here we are running the motor at low speed, and then we have the similar kind of results you can see. And here we have done the speed reversal. Okay, so initially the motor was running in the clockwise direction, and then we have done the speed reversal. Okay, so the speed will gradually come to 0, and then it will start rotating in the opposite direction, and you can see the phase reversal is happening here in the current and voltage waveforms. Okay, so in the previous method you can see the performance of the drive is dependent on that value of k damp. Okay, right? So then I thought of proposing some method where we do not need any damping gain. So for that, actually what I did actually, so I took the output of the PI controller, that is basically your inverter voltage reference, and this is also basically your so if you ignore the voltage drop across the inductor also, so this is nothing but your the filter capacitor voltage reference also. Now in case of filter capacitor, what is the capacitor current? IC will be equal to C dV by dt, right? Now we have this term, and if you do some differentiation here actually, so then you will generate some current, and that current we are feeding it forward to the to the current controller actually. So here in this case actually I am not sensing any inverter current. What we are doing, we are taking this V inverter X, then we are doing C dV by dt, we are generating some current here, and that we are adding in the reference of the current controller. Okay, the other structure that will remain same. Okay, and if you do so, then also you will have the same thing. So this is without this feed forward term. You can see that system is unstable, and the moment you have added this feed forward term, you'll see that all these things will be shifted from this side. Okay, and that also has been validated with the Bode plot also. So so without filter and without FF, with filter and without FF, and without filter and with FF, so you can see the phase margin and gain margin and so on. Okay, so I'm not explaining all this in details because I think we are running out of time. So now in this case you can see we are using a value of CF here. Okay, but in actual now this CF, the value of CF that we have taken means according to the value of the actual capacity that has used in the filter, but it may happen that because of some reason the filter capacity value may change also. So now we have done the analysis. If the filter capacity value changes, how it is going to affect the location of the poles and zeros at different operating conditions. So that also we have checked here. And yeah, and this is basically the final structure here. So here we are not sensing any inverter current or anything, just we are taking this term, then we are doing the differentiation, and then we are adding this term here. Okay, and here also you see that this is the stated performance drive with this feed forward term at different operating conditions. Okay, and here also we have checked the dynamic performance of the drive in the similar manner. Okay, here also we have done the speed reversal and so on. Okay, so in the first case, so this active damping technique that depends, so there we are sensing the inverter current, then we are doing DQ means ABC to alpha beta, then alpha to DQ conversion, then we are extracting the resonant frequency component from the inverter current, then we are multiplying the gain, and that we are adding at a compensating term. In the second case, we are not putting any extra sensors here, rather we are sensing the reference voltage, then we are doing the differentiation, and we are adding that term in the current reference. Okay, so these are two difference between these two techniques, and I have shown you the simulation results, all the analysis and the experimental results also. Okay, so so this is all about the discussion on the rotor flux oriented control of induction motor drive with and without filter, and you have seen that how the filter dynamics is affecting the dynamics of the rotor flux oriented control drive, and you have seen that because of the resonant frequency oscillations of LC filter at certain operating points the drive will be unstable. So how we can stabilize the operation of the drive at different operating condition through different active damping techniques. So that was demonstrated here. And then now I'll talk about some of the recent developments that happened in our lab actually. So in ATTC, I have developed one lab that is called Smart Power Electronics and Electrical Drives Lab. So this is an interface board that we have made here. So here also we have TMS320F2835 MCUs. Okay, and we have a lot of ADCs and other things. Okay, this is also a generalized board. You have a lot of PWMs, then you have 2-channel DAC, 8-channel DACs. Okay, you have multiple GPIOs and other things. So we have published one paper also here. So this paper talks about how we have developed this board, what are the different circuit components which are present in this board, and how you can do the programming. See, you can do the programming of this TI microcontroller two ways. Either you can write down the embedded C code in CCS, Code Composer Studio, that is basically IDE, and other way is that you can use the MATLAB to do the programming of this microcontroller. Okay, that is called MATLAB Simulating Embedded Coder. Okay, so you need to install some of the softwares. Okay, so if you install and which is freely available in the TI website, if you install the software actually, then like other simulating toolbox, you will also find one library for all these TI microcontrollers, and you need to take different blocks from the microcontroller to make your to implement the control logic. Okay, so if time permits, maybe I'll show you some of the things. So this is one development, and we also recently developed one of the silicon carbide inverter here. So here we are not using 28335. Here we have used 2837990 launchpad, TI launchpad. So initially I showed you one inverter, and now I am showing you another inverter. So so the basic circuits are more or less same, but the structure and other thing that we have changed. So here you can see all the gate drivers. They are vertically mounted, and they are quite modular in structure. And we have kept all the, and here there actually I put all the SiC MOSFET actually in one heatsink, but here you can see that for two MOSFET we have one heatsink. Okay, and here also we have tested this inverter up to 15 ampere RMS current. So 15, and also we have overloaded this motor so that we can go up to 20-25 ampere. And these are the motor line to line voltage and motor current waveforms here. Here I am showing the gate to source voltage and drain to source voltage waveforms, and these are the VDS of drain to source voltage of the lower side MOSFET during turn on and turn off operations. So these are some of the waveforms. So so this paper has been accepted in the National Power Electric Conference. So I'm not discussing all these things in details, because once that paper is published, then we can talk about all these things in details. but this is some of the things. And here also we have implemented the vector control at 50 kilohertz. Okay, these are some of the waveforms. You can see the IMR, then the speed waveforms, then current. Okay, and so this is without any LC filter. Only the rotor flux oriented control of squirrel cage induction motor drive, and that was fit from a PWM BSI, silicon carbide. Obviously, it was switching at 50 kilohertz, and its controller inner loop control bandwidth, it was around 5000 hertz actually. So the response are quite faster and so on. So these are two papers that was accepted. Okay, and the second paper actually, so when you do the parameter estimation for a induction motor, we do the no load test and block load test, and there we assume that, and the mathematical, when you do the mathematical modeling of induction motor in station reference frame, we assume that it's a star connected motor. But if you have a delta connected motor, okay, so without changing any physical connection, so how you can estimate its parameters, okay, and how you can find out, because those parameters are you require for if you are implementing the rotor flux oriented control of induction motor, because when you are estimating the slip speed here, there you will find that there is term called TR, that is called the rotor time constant. Okay, so it's nothing but LR by RR. Okay, so if you're, now what happened actually, so initially you have estimated the parameters from no load test and block load test, but as you are operating the motor for a long time, you'll see that the motor parameters are going to change, but in your microcontroller you have kept all the motor parameter constant, so there will be a parameter mismatch, right? So in that case, what people do, they basically do some adaptive online estimation of these parameters, and they use those estimated parameters in the control logic to compensate this parameter mismatch. Okay, so there are different techniques, and also one thing is, you see that in case of this one, this rotor flux oriented controller, we keep the IMR constant, right? We keep the IMR constant, but uh, but but you'll find that there is one technique that is called the energy efficient control of induction motor drive. Okay, so there actually, so you can vary this IMR depending on the operating conditions. Okay, instead of keeping this IMR fixed, if you vary this IMR to minimize the loss in the machines, so then you can realize the energy efficient control of induction machine. Means you try to operate the machine in such a way that you are reducing the copper loss and coal loss inside the machine. Okay, and there is another technique that is called the Maxian torque per ampere also. So let's say if you reduce the value of IMR, you will see the torque capability of the machine that will also reduced. Okay, so you need to ensure, now if you want to combine both the things, energy efficient control and also the Maxian torque per ampere control also, MTP also, so you need to select the value of IMR in such a way that you are also reducing the losses, as well as you are also providing sufficient amount of torque to the load, okay, to maintain the speed also. Okay, so here, so in this control actually, in case of induction motor actually, so you can use this AIML technique for let's say for the parameter estimation of the motor also. There you can use some AIML technique. Let's say here I am using some PI controller, right? KPKI, these are fixed value. Okay, but as I've told you that the moment the motor parameter will change, the transfer function of the plant, that will itself change. Okay, so the KPK value that we have selected initially, so now that may not be the perfect one for the changed parameter conditions. Okay, so how you can change the value of KPKI by using some AIML algorithm. So that is also another area also, right? And in case of, let's say, this energy efficient control, how you are varying the value of IMR and so on. So there also you can use these things. Okay, so yeah, thank you so much for the things. And let's say maybe,
Thank you, sir.
yeah, so do you have some time, let's say 5-10 minutes?
Yes, sir. If you
Or
want to carry on, you can carry. No issue.
just I want to show you something actually. So
Yes, sir. Sure,
regarding,
sure.
okay, just 1 minute.
Sure, sir.
Okay, So actually, so as I told you that how you can do the programming of this TI microcontroller through MATLAB actually. So what you have to do, I quickly cover this slide actually. So you need to open this MATLAB and then you need to click on this add-on here. Okay. Then if you click on this add-on, then one window will open. So this is embedded coder support package for Texas Instruments C2000 processor. If you
So
click
sorry
here
to
actually,
interrupt. If you are
yes.
sharing something, we can't see actually. You can
Okay, sorry.
see only your
Okay.
thank yous, right? So sorry to disturb you. Sorry so much.
Okay. Just hold on.
Sir,
Let,
you can
let
share your entire screen, sir.
yeah.
Where it will be
Just
visible.
okay. Fine. Okay. Okay. So yeah. So what I'm trying to now how just open the MATLAB actual window, then click on add-ons here. Okay. Now if you click here actually, then what will happen? So one minute. The slide slow. Okay. So this window will open. Then you click here. Then you will install the software by the following steps. So you need to follow these steps. Okay. Just then this embedded coder support package for Texas Instruments C2000 processor. Okay, then click on the setup, do the following steps. So here actually you have the option for this TI microcontroller have different series of microcontroller, right? So if you want to include all the, let's say the library for all the components, then you select all. In other case, you can specifically select the microcontroller. Let's say if you're using 283790, then you should click here TI Delfino F2837XT. Okay, for 28335 also you can select.
Still, it is not visible, sir.
Still, it is not visible.
No,
Can
sir,
you?
it's not visible.
I have shared the entire slide. Just I don't know what is happening. I have shared the entire screen actually.
Okay.
Can you see my screen?
Hi, yes, your screen is visible. Now you can maximize
Now,
that.
is it visible?
Your
Can
screen
you
is
see my
visible,
slide?
computer screen. Yes,
No,
yes, yes. Now it's visible.
Yeah, it's
Now
visible,
okay,
sir.
visible.
Can you please start from step one?
Step
Then
5,
sorry.
yes, visible.
okay, fine.
Visible, sir.
Okay, so this is the select all option, and then you can install multiple packages here. Okay, and then there are certain steps. Some noises are coming. Just please mute yourself. Okay, yeah. So you need to follow these steps to
One
download the
second.
softwares and everything, and then if you follow these steps, finally you need to click here this open simulink, and you'll see there on the left hand side you have all the boards. Okay, you can see all the options will be here, and then from here actually you need to drag down the different blocks. So then I'll show you on one things here, maybe this one. Okay, so here I'll show you some of the very can you see my slide?
Yes, sir. We can
Your
see now.
screen is
Yes.
visible, sir.
The content example one GPIO, you are able to see?
Yes, yes. Speed measurement, yes, it is showing.
Speed. Okay, fine. So here I'll show you very simple example. So let's say this GPIO block actually that you can get it from the that matter library actually. So here what we are trying to do actually, so we have taken one GPIO digital output block here, and we have configured this block here. Here we have specified that we are using GPI. We are configuring GPIO 40 as output pin here, and at the input we are giving a pulse. Okay, and at this particular GPIO pin we have connected one LED here, and the moment you will apply the pulses here, actually what will happen, this LED will glow based on these pulses. Okay, so here I'll show one video here. You can see this LED is blinking. Okay, so if you can do this simple exercise actually, so you'll come to know that how you can configure one GPIO block either as an input pin or an output pin also. Okay, so this is one example that you can think of to configure the GPIO. Okay, so here I am showing you the very basic example to configure the different blocks. So this is one example on GPIO. Okay, so then the second example was on enhanced pulse width modulation. So this is the EPWM block which is available in the this TI library. Okay, and here we are doing the sinusoidal pulse width modulation. That's why we have taken one sine wave from here, and the modulation index was 0.9 here, and we are multiplying with some gain here, that is 19,999. Actually we need to calculate. So there is one register that is called time-based period register. We need to find out the value of TBPRD actually. And then how do you configure this block? So this is the configuration for the sine block. This is fine. And here you need to give only the positive voltage. Okay, so here you can see initially we have taken one 0 to 0.52 plus minus 0.5 sine wave, and then we have added one DC offset here, so it will become 0 to 1, and the frequency is 50 hertz because it is in radian per second. The sampling time is, this is fine. And then when you are trying to configure this EPWM block, actually you have multiple tabs here. Okay, so as the time is limited, I am not able to cover all these things, but at least maybe if you have some if you have time sometimes later on, maybe you can go through all these things. So here are multiple tabs actually. So here you need to put different values, you need to configure in different way. Okay, so this is the for the EPWM1. Similarly, in the module section, you have in the drop down list you have EPWM1, 2, 3, 4, 5, 6. And this TBPRD value that you need to calculate here and you need to put it here. Now there are different counting modes, either up count, down count, up down count, and so on. So and then here you need to configure A and B. So if you want to generate the complementary pulses, then you need to set clear set, that you have to do. Then you have a dedicated unit for the deadband. Let's say you want to generate 2 PWM signals, but they will have the deadband from the software side, so that also you can configure here. Okay, so this is the thing. Then I'll show you one video here. So here you can see, so this is the we have generated 2 gate pulses from the EPWM1, 1A and 1B. You can see that we have put the date time here, and you can see that at any moment 2 of the switches are not turned on simultaneously. And here I'll show you on video. So here we are doing the sinusoidal pulse width modulations. Here you can see the width of the pulses varying based on the sinusoidal reference voltage. Okay, and then there is one example on DAC. Okay, so here actually what we are doing here actually, so here we are doing the loop back test here. Okay, so here we are doing the loop back test. So from the we have connected one signal in the ADC from a signal generator, and so from the ADC block that is connected to the DAC block. Okay, so now if you have configured this ADC and DAC block accurately, so then your input signal and the DAC output, they should match each other, right? So this is how you can configure this block. So, and I'll show you another video here. You can see this blue color one is the ADC input and this pink color one is the DAC output. So this is called a loop back test. Okay, you are taking one signal in one of the ADC pin and you are sending it out to a DAC pin. Okay, and we are observing those 2 signals in the oscilloscope. You can see, so they are matching with each other because the scales are also same. So yeah, and then you can also so in this example actually what we have to initially we took one fixed frequency, fixed sine wave, but here we have also connected one ADC block by which we are varying the modulation index of the sine wave actually, and we have done the EPWM here. We have generated the pulses here. Okay, so here I'll show you the video. You can see the more you are increasing the modulation index, you can see the width of the pulses are increasing. Okay, this blue one is basically the your ADC, the output of the ADC, and this is the width of the pulses. It is varying. You can see here. And you can also, so in these microcontrollers they have one QEP module. Okay, so you can configure this module to estimate the speed. Now if you look at any encoder, actually you have 5 wires will come out. One is A pulse, B pulse, and Z pulse. Z is called the index pulse. And in the A pulse and B pulse you will have 2 pulses, but they will be 90-degree phase shifted. You need these 2 pulses to find out the direction of the motor. Either it is rotating the clockwise direction or anti-clockwise direction, because one of the pulses will be leading or lagging as compared to the other pulses. Okay, so there is one dedicated block that is called EQP block. So you need to configure this block to estimate the speed of the motor. So you need to do some calculation in between. So it will take some time to explain, but okay. Anyway, so this is how you can do it. Okay, so here what we have done actually, so we have connected an encoder, and then in the MATLAB we have taken this block, we did some calculation here, and through a DAC actually we are so we have estimated speed here, and we are sending in back out of the microcontroller through a DAC pin. Okay, and this is how you can configure those blocks. Okay, and you can see there. So this is the estimated speed. This is that output of DAC, and we have also measured it to through a tachometer also, and they are matching with each other. Okay. Yeah, thank you for your attention. So I have showed you few examples so that at least if you can try something with this basic example, and later on you'll find that when you are trying to implement any motor control logic actually, so effectively you have to use some EPWM blocks, you have to use ADCs, you have to use GPIO, you have to use interrupt, okay, you have to use DAG and so on. Okay, if you know how to configure each and individual block, the rest of the things will very easy for you for real-time implementation. Okay, so thank you so much. I think I am 20 minutes late around. Sorry for the delay. Yeah.
No, sir, it is very nice and very interactive session. So it's very good, really good. I think
Yeah.
we are able to know a lot of things from your presentation, sir.
Yeah. So as the
From
time is
the
limited actually, so I could not cover many of the things, but
yes, sir.
what can I
Okay,
do?
sir. Okay.
Okay.
Next time, definitely, sir, we'll discuss with the pending portion, sir. Thank you, sir. Any very quick interaction with the participants within 5 minutes? Any queries? Any if you want to ask anything to the professor, if you want to ask them.
If you have any
Hello, am I
questions, so
audible?
yes, I can hear you. Yeah, please.
Okay, you presented that controller design for a PA controller design for the current
Yes,
controller and the speed controller.
yes,
Later, you included the effect of that LC filter. Then you
yes,
considered that small signal modeling of that. Okay.
yes.
So what is the criteria for selecting the small signal model? Because prior to that, we have not considered small signal modeling, but later you
Okay.
included that.
Because see, if you look at this dynamic equation, so they are non-linear actually. They are non-linear actually. So that is why to linearize those non-linear equations. So and because I wanted to represent that system in the state space. Okay. So if I want to represent that system in the state space, what I have done actually, I have done the linearization through the small signal analysis, and then I have written down all the equations in the state space, and from the state space representation, I have find out the transfer function. And then I have used the transfer function to find out the closed loop transfer function when you are inserting the filter. What it will do actually, it will modify the initial planned transfer function of the motor. Now the that transfer function, it will include motor as well as filter also. But the thing is that linearization is valid only at that operating point. Okay, because if you look at that A matrix actually, so you have some term, steady state term are present, which is very related to that operating point actually. Okay, is it okay for you, or should I explain further?
Anyway, the small signal components are also passed through the motor, right? And while modeling the motor, these are necessary. This motor model, we have not considered small signal analysis for modeling.
Yeah. So the small signal analysis has been done for both, means for the combined system, motor as well as filter also. For the combined system, it has been done to represent all the equation in the state space form. And these analysis is valid at an operating point. Now, if you change the operating point, obviously your A matrix and B matrix, that will change. Okay, because in earlier paper actually, so people what they have told that if you use a LC filter, because the filter resonance, so you will have some resonance frequency oscillations and your drive will not operate perfectly. But during my PhD actually, what I did actually, I have tried to prove it mathematically also, that how the resonance phenomena in LC filter is affecting the dynamics of the drive. Okay, as you can see that if you look at that these poles and zero, actually because the resonance phenomena, it is shifting the pole from the left hand side to right hand side actually, and the location of these poles are exactly at the resonance frequency. Okay, So that thing, and it will also help you in the stability analysis also. This all these equations also. But I cannot
Thank
say
you, sir.
but I cannot say that the system is globally stable also, because we can do the stability analysis at that operating point, because we have done the small signal analysis at that operating point. Now if you change the operating point, obviously the transfer function will change, because the A matrix and B matrix, that will change. Okay, so we can do the stability analysis at different operating points. Okay, now I cannot ensure the global stability. Okay, so if you want to ensure the global stability, then you can go for some means Lyapunov stability criteria and so on. So in that case, you do not linearize the overall combined system. You stay in the non-linear model and you do some stability analysis also. That also you can do.
Okay.
Yeah. Any other questions from the audience?
Is there any other questions from the audience here? Okay. I think there is no other queries. So thank you, sir, for giving us your valuable time. And it's really sorry, and it's really very nice because you are talking so much thing from last more than I think around 2.5 hours. So I think it's a huge and it's a very good that we are able to understand a lot of things from your side, sir. And we are
Okay. Yeah.
looking
Thank you so much.
forward for your any next interactions as soon as
But I
possible.
think it was too much
Okay.
for the participants. They had to wait
Yes,
at least
sir.
another 30 minutes
I,
more.
and no, that's good because I think we are able to learn a lot of things from that thing. Okay,
Okay.
because okay, anyway, thank you, sir.
Okay. Yeah.
Thank
Thank
you.
you. Thank you so much for the opportunity. And then, yeah. So if you have any queries or anything, then you can drop me an email and then we can discuss also. Means if somebody is having any question because of time, you are not able to ask me, so you can drop an email and we can discuss later on. Okay. So with this, I think
Okay, sir.
I'll conclude the sessions and then. Okay, Arnav?
Okay, thank you, sir.
Okay.
Yes,
So
sir.
I'm
Thank
leaving,
you,
yeah?
sir. Yes,
Okay,
bye.
okay. Thank you. Bye. Bye.
Yes, sir. Yes, sir. Bye. So, thank you for attending our second session of third day of our workshop. So we can go for some lunch break. Okay, and we'll join by 3 p.m. Okay, our next session will start from 3 p.m. Okay, okay. Thank you. In, now we can take a break. Okay, bye.
Do you want to go